All right. So this time we are going to do something kind of strange. We will cover sections 11.3, 4, 5, 6 all in one shot. Okay. Uh, what do these sections cover? They cover basically how to test whether a series converges or not. That's all you are going to ask. Hey, given a series, does this converge or not? We have many ways of figuring that out. Okay. Of course, you might ask, who cares? I mean, so you're just going to figure out whether the series converges or not? What good does that do? It does plenty of good, because if we know the series converges, then we can always write a computer program to figure out exactly what that sum would be, or at least not, even if it's not exactly, at least to a very, very good approximation to whatever tolerance you want, we can figure out. But for that, like I said, the series has to converge. A diverging series, if we know the series diverges, then we can just simply say, nope, series diverges, dude, so I'm not going to figure out what the sum would be. Right? It's a very important one. So let's look at this. Yeah, by the way, you will see a PDF document called test4series.pdf. Please be sure to take a printout of it and keep it next to you as we go through the rest of this. Okay. What else should I need to tell you that right now I'm just going to give you probably just one example of each test that we are going to learn. Okay. That is because I just want to get your feet wet, and after that there's a handout with 140 problems. We are going to solve 140 problems. You are going to, I'm going to solve a few of them to show you how it works, and you would have to solve all the 140 problems. It's a wonderful exercise, trust me. So if you learn in this course, if you learn integration really well, and if you learn the series part really well, you have done a lot. These are the two most important chapters in this whole course. So without much further delay, let's go on. Determine whether the given series converges or diverges by applying a suitable test. So let's say something like this. I will tell you that we need to apply integral test to this one. Why, how, let's not worry about that. So if you look at the handout, test for series, one of the things that you see, the very first one is a divergence test, and the second one is the integral test. So that integral test is what we need to apply for this particular problem. Okay, our intention is to figure out whether the series converges or not. I'm sorry I don't have it as a statement here, but if you were to have that, if you keep that handout next to you, you will see the integral test. Let me read as to what it says. Suppose f is continuous, positive, decreasing function on 1 to infinity, and let a sub n equals f of n. Then the series sigma n equals 1 to infinity a sub n is convergent if and only if the improper integral 1 to infinity f of x dx is convergent. So if, in other words, it says, point A, if integral 1 to infinity of f of x is convergent, then the series is convergent. If that integral is divergent, the series is divergent. What does that got to do with this? Here is the idea. Here, a sub n is 1 over n natural log of n. Would you agree with that? All right. Then we need to come up with think of this as f of n. f of n is 1 over n natural log of n, which is the same as a sub n. So what is f of x? Simple. Replace the n with an x. 1 over x natural log of x is your f of x. Cool? So f of x is 1 over x natural log of x. And the next thing is, if you look at the test, it says, oh, suppose f is continuous, positive, decreasing on 1 to infinity, it says, but here since we are going from n equals 2 to infinity, how come n is not equal to 1? That's because natural log of 1 is 0 and you do not want a 0 in the denominator. So this f of n would be undefined for n equals 1, and so we are safely starting at n equals 2. Cool? Okay. We first note that f of x is 1 over x natural log of x. Is it positive on 2 to infinity? Trust me, it is positive. Is it continuous? Yeah. If you don't believe me, well, plot it. Use your calculator or something like that and plot this one. You will see that it's continuous. And decreasing, that is almost obvious because you got just 1 on the top and x is increasing and natural log of x is also increasing. So 1 over something, some quantity that is constantly increasing. So therefore that ratio should decrease. So positive, continuous, decreasing. So all those requirements are satisfied. So we can apply the integral test. Okay. Now, all we need to do is figure out this particular integral 2 to infinity 1 over x natural log of x dx. What's the idea behind figuring out this integral? Like the test says, if this integral converges, our series converges. If this integral diverges, our series diverges. As simple as that. So, let's see. How do we figure out this integral? Well, substitution. U equals natural log of x and du is 1 over x dx. So this is basically du over u, and in other words, this integral turns out to be natural log of x. Natural log of u, natural log of absolute value of u. I'm not using absolute value here because we know u in this context is going to be positive for 2 to infinity as x takes on values from 2 to infinity. Natural log of x will be positive, so I don't need an absolute value around that. So this is just natural log of x, 2 to infinity. Wait a minute. So can we simply plug infinity? Don't do that. Don't say I'm going to plug infinity for x. That'll give a mathematician a heart attack. Instead, you simply change it to, in order to apply the upper limit infinity, we are going to figure out limit as x approaches infinity. Cool? So limit of x approaches infinity of natural log of x minus, now you can plug in 2, that's not an issue, right? Plugging in 2 for x is perfectly fine. So minus natural log of 2. So now the question is, what in the world is limit of natural log of x as x goes to infinity? Well, as x goes to infinity, natural log of x goes to infinity. Natural log of something that is going to infinity would also be infinity. So this whole thing is just infinity. So the limit is equal to infinity. In other words, this whole thing is equal to infinity. In other words, this series diverges. Right? Since the integral diverged, we can confidently say the series also diverges. Cool? So, wait. What sigma 1 over n natural log of n diverges? Yep, that's what we found. I find that incredibly fascinating. Why? We know that sigma 1 over n, which is the harmonic series, that diverges, right? But we also learned that sigma 1 over n diverges very, very slowly. For example, for the sum of a harmonic series to add up to, say, 2001, we need to, or 1001, we need to add 2 to the 2000 terms. I showed you something like that, right? If you want the sum of a harmonic series to be just slightly greater than, say, 1001, you must add the first 2 to the 2000 terms, which is just a ridiculously high number. But you have to conclude that the harmonic series diverges. Guess what? These terms are in fact smaller than the terms of a harmonic series. 1 over n natural log of n, right? So the 1 over n natural log of n is actually less than 1 over n for all n greater than or equal to 2. So these terms are smaller. Now, what's the big deal about that? Imagine the ramification of that. This series will diverge even more slowly than the harmonic series itself. We already established that harmonic series diverges ridiculously slowly. And this one apparently diverges even slower than that. Right? Okay. Okay. So the question is this the slowest diverging series? No. If we apply the same test, we can show that 1 over n natural log of n, natural log of n. What am I going to do? I'm going to add in the sense multiply the denominator by a natural log of n. If I do, this integral for that one turns out to be natural log of x. And guess what? That also diverges. As x goes to infinity, that is going to go to infinity. So 1 over n natural log of n is also divergent, and it diverges even more slowly than this guy, right? So that's just mind-boggling. Well, is that the lowest? No, it's not. You can keep on multiplying by nested natural logs. Natural log of n, natural log of n, natural log of n times natural log of I lost count of it. Right? That's going to be even slower than the previous one. And so on. So that's a fascinating aspect of it. All right, let's move on. Yeah, this is a good one. This is an important one. P is just a real number. So sigma 1 over n to the p, where p is greater than 0. Yeah, I need to say that. Okay, so p must be greater than 0. That's all the stipulation is. It could be any real number greater than 0. And we will apply the integral test to this also. So that means we need to come up with what f of x would be, which is 1 over x to the p. And if p is greater than 0, then 1 over x to the p would be positive, continuous, and decreasing on 1 to infinity. And that fact satisfies all the requirements of this one. So let's figure out this one. This is a straightforward rule, power rule of integration. X to the negative p plus 1 over negative p plus 1. And again, to apply the upper limit infinity, we will actually calculate the limit as x approaches infinity of this quantity. So the question now becomes, what in the world is this limit equal to? Limit as x approaches infinity of x to the negative p plus 1. Well, if that exponent negative p plus 1, if that happens to be negative, let me make a simple number, negative 2. If the exponent happens to be negative 2, when would that be? When p is equal to 3, you have negative 3 plus 1 is negative 2. So let's say p equals 3, making the exponent negative. Then we have limit as x approaches infinity of x to the negative 2. X to the negative 2 is the same as 1 over x square. So limit of 1 over x square is clearly 0, right? As x approaches infinity, 1 over x square has to go to 0 as x goes to infinity. What else? In fact, for any value of p that is slightly greater than 1, that is greater than 1, it doesn't have, yeah, let me put it that way. Any value of p greater than 1, this limit goes to 0. If not, if we are talking about any value of p between 0 and 1, we already said p must be greater than 0. So any value between 0 and 1, a p value of 0 and 1, then this limit is going to be divergent, or this limit goes to infinity, and so this would be divergent. So we will conclude that this would simply be, in the event where this limit goes to 0, we have 1 over negative p plus 1 times negative 1, which makes it 1 over p minus 1 whenever p is greater than 1. And for all the other values, that is p is between 0 and 1, this integral would diverge. So the integral 1 over x to p of 1 to infinity converges when p is greater than 1, which means when we go to the series, we can do the same thing. The series sigma 1 over n to the p converges whenever p is greater than 1, strictly greater than 1. What does strictly greater than 1 mean? Or what's the difference between strictly greater than 1 and greater than 1? Mathematicians, sometimes when they say greater than 1, they mean greater than or equal to 1. But if they say strictly greater than 1, then cannot be equal to 1. That's the whole idea. Must be greater than 1, cannot be equal to 1. So that's why we say strictly greater than 1. Anyway, so here this series sigma 1 over n to the p will converge whenever p is strictly greater than 1. That is the lesson. And a series of this form, sigma 1 over n to the p, is called a p series. Cool. We'll use this p series quite a bit. It's a simple one, but it comes in very, very handy, right? So here, converges when p is greater than 1, diverges otherwise. Let me use that concept to ask you a couple of questions. What do you think about sigma 1 over square root of n? Wait, is this a p series? Yeah, because I can rewrite this as sigma 1 over n to the 1/2. So p happens to be 1/2 in this case, and 1/2 is less than 1. Guess what? We don't need any other analysis, any further analysis. We just simply say this series diverges. Why? Because this is a p series with p equals 1/2 less than 1, and so we can say series diverges. End of the story. Cool. How about this one? Is this a p series as well? Yeah, if we can write this n times square root of n as n times n to the 1/2, in turn that is equal to n to the 3/2. Yeah, this is a p series because it is in the form of sigma 1 over n to the p. P happens to be 3/2. P happens to be 3/2, which is greater than 1. That's it. So that series must converge, right? Simple. Notice how simple this becomes. And now let's move on to another one. Let me go back to this one. Are we cool? All right, what about, let me quickly ask you, what about sigma 1 over n square? That must converge, p equals 2. What about sigma 1 over n? P is equal to 1. We already know that's a harmonic series, right? P equals 1. It gives us a harmonic series which diverges. Keep that in mind. Cool? All right, let's move on to the next problem. And here I'm going to try to illustrate what is called a comparison test. So keep that handout handy. Look at the comparison test. I'm going to apply that for this one. Okay. What does the comparison test say? Suppose that sigma a sub n and sigma b sub n are series with positive terms. Sigma a sub n and sigma b sub n are series with positive terms. Okay. If sigma b sub n is convergent and a sub n is less than or equal to b sub n for all n, then sigma a sub n is convergent. And part B says if sigma b sub n is divergent and a sub n is greater than or equal to b sub n for all n, then sigma a sub n is divergent. Right? So that's what the test says. Apparently, we need to apply that test. Wait a minute. The test talks about some sigma a sub n and sigma b sub n. What are sigma a sub n and sigma b sub n? Here is the idea. The given series is always sigma a sub n. Okay, in our case, what is sigma a sub n? This is sigma 1 over n square plus n. Cool. And the series that we use to compare this series with, that is the sigma b sub n. Now the question is, what do you mean by use some sigma b sub n for comparison? What is that? We need to figure that out. Okay, we choose sigma b sub n and do so such that these are the points that must be satisfied. Number one, when we pick a sigma b sub n, we should be able to quickly, fairly effortlessly figure out whether that our sigma b sub n converges or diverges. If you don't know, or if you cannot figure out as the convergence or divergence of a sigma b sub n, then do not pick such a sigma b sub n. Okay? So, something that you should be able to figure out. Cool. And then, we should be able to fairly easily compare the terms of a sub n and b sub n. 1 over n square plus n, whatever b sub n we pick, we should be able to easily compare that. Okay? So, we recognize that a sub n is 1 over n square plus n. What should we choose for sigma b sub n? Well, excuse me. We should, maybe I'll get a drink of water and in the meantime let you think of what you think you could use. Okay. I would say sigma 1 over n square. The question is, does this sigma b sub n satisfy the two requirements? We can easily determine the convergence divergence of sigma b sub n. Can we tell if sigma 1 over n square converges? Of course we can. It's a p series with p equals 2 greater than 1. So, very effortlessly we could tell that sigma b sub n converges, right? That was the idea. And the second point is, can we easily compare the terms of a sub n and b sub n? 1 over n square plus 1 n and 1 over n square. Can we compare? Of course we can. 1 over n square plus n is clearly less than 1 over n square for all n in the natural number set. That's just a fancy way of saying for all the values of n that are equal to 1, 2, 3, 4, 5, 6, and so on. n for all, that inverted v is for all, n is an element of natural number set. Okay. Let's see. I pretty confidently said, yeah, 1 over n square plus n is less than 1 over n square. Is that really true? Yes, it is. How do we know that? Notice that these two fractions have the same top but different bottoms, right? The one with a bigger bottom has to be a smaller ratio. Kind of like if I have 1/2, compare that with 1 over 100. 2 is smaller than 2 is smaller than 100, or rather, I think in this case I'm trying to go the opposite way. 100 is bigger than 2. So 1 over 100 is just a small 0.01, whereas 1/2 is 0.5. So with the numerators being the same, if the one with the bigger denominator is going to be smaller. And clearly, n square plus n is greater than n square. So this ratio must be smaller than 1 over n square. That's the idea. Okay, now look at the comparison test in the handout. What does it say? Suppose that sigma a sub n and sigma b sub n are series with positive terms. Let's first make sure that we satisfied that requirement. Would you agree that sigma, this terms 1 over n square plus n is always positive for all values of n equal to 1, 2, 3, 4, and so on? Good. How about 1 over n square? Are those terms positive? Yep. When n takes on values of 1, 2, 3, well, in this case, it doesn't matter whether n is positive or negative. N square is always positive. 1 over n square is always positive. Cool. So we satisfied the condition that sigma a sub n and sigma b sub n must be series with positive terms. Is sigma b sub n convergent? Yep, it is. And did we show that a sub n is less than b sub n for all n? Yes, we did. Guess what? Since sigma b sub n converged and a sub n is less than b sub n, we can now say sigma 1 over n square plus n, our series, also converges. Does it kind of make logical sense as to why a series with smaller terms should converge? Yeah, the terms of 1 over n square are bigger than the terms of 1 over n square plus n. And these bigger terms themselves added up to a nice finite number. That's what converging series means. So these terms, when you add up all the infinite number of them, of this series, that ended up being a finite number. So it stands to reason that all these terms, which are even smaller than that, should add up to a finite number. That's the concept, right? Are smaller than, yep, that's what I wanted to say. Cool. Next. What about sigma 1 over n plus 3? Let's see. Can we apply comparison test with sigma b sub n equals sigma 1 over n? Let's see. The thing is, I'll let you look at this one. What do I mean by this? No, because sigma 1 over n diverges as a harmonic series, but the terms 1 over n plus 3 is less than 1 over n. I'm trying to convey a very, very, very important point here. If what you're comparing with, that is the sigma b sub n, happens to be a diverging series, which it is in this case, the terms of your series, they better be bigger than the terms of the diverging series. If that is not the case, as here you can see that that is not the case. 1 over n plus 3, these terms are less than 1 over n. You cannot use comparison test. You would have to resort to some other test, but the regular comparison test you cannot use. Is that clear? You have a diverging series, your terms better be bigger than the diverging series. In the same way, if you are comparing with a converging series, your terms better be less than the converging series. Key point to remember. Okay? All right. So, yep. So note, for comparison test, if sigma b sub n is convergent, the terms a sub n must be less than b sub n. And then we could conclude sigma a sub n converges. On the other hand, if sigma b sub n is divergent, this is the idea, right? So we cannot apply this one, the regular comparison test. But if you look at the handout, right after the regular comparison test is what's called the limit comparison test, right? We can apply that one. What do we pick for sigma b sub n? Again, remember the two conditions that sigma b sub n that you pick should satisfy. You should be able to readily figure out whether or not your sigma b sub n converges or diverges, right? Does this sigma 1 over n satisfy that? Yeah, it's a harmonic series which diverges. So that's satisfied. And then, can we easily compare this 1 over n plus 3 with a 1 over n? Yeah, we can. And so, we will, let's look at that. Yeah, what exactly is the limit comparison test? Let me read that. Please look at your handout. Suppose that sigma a sub n and sigma b sub n are series with positive terms. 1 over n plus 3, positive terms? Yep. 1 over n, positive terms? Yep. So we are good. Apparently what we need to do is, or please, if limit of a sub n over b sub n is equal to c as n approaches infinity, where c is a finite number and c is greater than 0, then either both series converge or both diverge. So that test tells us that after we pick a sigma b sub n, we will now need to figure out limit of a sub n over b sub n. That's exactly what we are doing here. Limit of a sub n over b sub n as n approaches infinity. And a sub n is 1 over n plus 3. We need to divide that by 1 over n. Typically, I don't divide by 1 over n. I multiply by the reciprocal of that. Right? So, the question is, what is this limit? I should have put a bracket or a parenthesis around this because I'm giving the impression that I just have limit as n approaches to 1 over n plus 3 and then I'm multiplying that by n over 1. No, I don't mean that. I'm talking about the limit of this product. Okay, so that is equal to, what is that equal to? Well, would you agree that we have a polynomial over a polynomial, same degree polynomial, first degree polynomial on top, first degree polynomial in the bottom. So ratio of leading coefficients, coefficient of n is 1, coefficient of n in the bottom is also 1. So this is just 1. And 1 happens to be greater than 0 and is also finite. So we can now say both, according to this test, either both series converge or both diverge. We already know that sigma b sub n diverges, so our series must also diverge, right? That's the idea. Cool? All right. Next. What about this one? I picked this problem to talk about what is called the alternating series test. Take a look at the handout. It says the alternating series test. The alternating series sigma n equals 1 to infinity, negative 1 to the n minus 1 b sub n is equal to b1 minus b2 plus b3 minus b4 plus b5. I have a typo there. Should be minus b sub 6, and so on, right? With b sub n greater than 0 satisfies two conditions. B sub n plus 1 is less than or equal to b sub n for all n, and limit of b sub n is equal to 0. So that is, then the series is convergent. So let's see. Is this an alternating series? What is an alternating series? A series with alternate positive and negative terms, as simple as that. So if a term is positive, the very next term must be negative, and the one after that must be back positive, and so on. So either you have positive, negative, so on, or negative, positive, negative, and so on. That's an alternating series. So sure enough, this, when expanded, you have 1 minus 1 half plus 1/3 minus 1/4, and so on. Cool. So this is an alternating series, and we'll try to apply the alternating series test. Okay. Such a series with alternating positive is called an alternating, and this particular series is the alternating harmonic series. Our regular harmonic series was 1 plus 1 half plus 1/3. Now this is an alternating series, and it's an alternating harmonic series. Here is one important thing I want to convey. Every alternating series will have one of these forms. Either your a sub n is either negative 1 to the n minus 1 b sub n, or negative 1 to the n b sub n. Okay. Every alternating series, the moment you notice that the terms are positive and negative like that, it has to be, a sub n has to be either this form or this form. Which form is ours in? Clearly the first form, negative 1 to the n minus 1. Would you agree? Wait a minute. What is b sub n though? Our a sub n is negative 1 to the n minus 1 over n. And this one says this is a sub n. So what is b sub n? Would you agree it should be 1 over n? Yes. So our series is of the form negative 1 to the n minus 1 b sub n, with b sub n being 1 over n. Okay. Now, what does it say? Immediately figure out limit of b sub n. Is that equal to 0? Yep, it is equal to 0. And is it the case that 1 over n plus 1 would be less than 1 over n for all n in the natural number set? Can we confidently say that that is the case? Yeah, we can, because notice n plus 1 is a bigger denominator than n itself. So as a fraction, that must be less. So if you look at the test, b sub n plus 1 must be less than or equal to b sub n, which is true here. And limit of b sub n happens to be 0. So we have both conditions satisfied. So we can confidently say that this alternating harmonic series converges. All right. Well, it looks like I'm picking only one example in every one of these things, but trust me, I'll show you quite a few examples once I start picking up problems from the 140 problem set. And I'll show you how to apply each one of these tests via many examples. So if you didn't quite completely grasp every little aspect of whatever I'm doing here, don't worry too much about it. We will get everything squared out. Okay. Oh, by the way, yeah, that's an alternating harmonic series converges. Ooh, yeah, keep this in mind. Harmonic series itself diverges, but the alternating harmonic series actually converges. Now, that takes us to a few definitions. Sigma A sub n is absolutely convergent if sigma absolute value of A sub n is convergent. What? Let's say you have a certain series, sigma A sub n, right? That's usually your given series, sigma A sub n. Now, if by some chance you look at a series with absolute value of A sub n, once you know A sub n, figure out absolute value of A sub n and make a series out of that and ask, does that series converge, sigma absolute value of A sub n? If that converges, you will say that the original series is absolutely convergent, meaning even if I were to take the absolute value of the terms, that series also converges. A second definition. Series sigma A sub n is conditionally convergent if sigma A sub n is convergent, but sigma of absolute value of A sub n is divergent. What does that mean? We would say that a series sigma A sub n is conditionally convergent if it so happens that the series itself converges. But the moment you take the absolute value of the terms, that series diverges. Okay. Do we know of any conditionally convergent series? Right? Think about it. If you said the alternating harmonic series, you are absolutely right. Pat yourself on the back. How? When we look at the alternating harmonic series, A sub n happens to be negative 1 to the n minus 1 over n, right? We saw in the previous one. Did that series converge? Yes, it converged. So sigma A sub n is convergent. But if you were to take the absolute value of negative 1 to the n minus 1 over n, you just get sigma 1 over n. That is a harmonic series which diverges. And that's why we say the alternating harmonic series is conditionally convergent. Okay? Cool. Now let's look at another very important theorem. If a series is absolutely convergent, then the series is convergent. I'm not going to prove this and all that stuff, but this is an important theorem. In the sense, if by some chance you were to look at the absolute value, sigma of absolute value of A sub n, and you find that when you take the absolute value, the series converges, you can be confident that without taking the absolute value, that series also would converge, is the issue here. Okay. Can you think like a teacher and ask yourself a question? This one says if sigma absolute value of A sub n is convergent, then sigma A sub n is convergent. What if I were to change convergent to divergent? Can we say if sigma, if sigma absolute value of A sub n is divergent, then sigma A sub n is divergent? Can we say that based on this? The answer is a big no. A big no. Because we have a counterexample here. The alternating harmonic series was convergent, but the moment you take absolute value of it, you get the regular harmonic series. The regular harmonic series diverged, but the alternating harmonic series did converge, right? So you cannot change this to counterexample. Yep, this is what I was talking about. Right. So the converse is false. If the converse is if a series is convergent, then the absolute value of that series, sigma absolute value of A sub n is convergent, is definitely false. And yeah, let me not spend too much time on it. There's something called inverse, and I don't want to get into that. So this is a conditionally convergent concept. One more problem, I think. one more problem. Oops. Let me do this and we are done. How about this one? If you look at the handout, there's something called the ratio test. I'm just going to apply the ratio test for this one. What is the ratio test? Ratio test, if limit of absolute value of a sub n plus 1 over a sub n as n approaches infinity equals L is less than 1, a series is absolutely convergent and therefore convergent. And if this limit happens to be greater than 1 or infinity, then series diverges, and equal to 1, inconclusive. So for the ratio test, everything seems to hinge on us figuring out what limit of absolute value of a sub n plus 1 over a sub n is. Okay, so apply ratio test. So that means you figure out what is limit of absolute value of a sub n plus 1 over a sub n as n approaches infinity. Wait, what is a sub n? Yeah, in this case, a sub n is 2 to the n over n factorial. Okay, if I know a sub n to be 2 to the n over n factorial, can I figure out what a sub n plus 1 ought to be? Yep, simple. How? Replace the n with an n plus 1. Cool. So, a sub n plus 1 would be 2 to the n plus 1 over n plus 1 factorial. So that's what we're going to put. 2 to the n plus 1 over n plus 1 factorial. We need to divide by a sub n instead of multiplying with the reciprocal of that a sub n. That's all I'm doing. So the question is, what in the world is this limit equal to? So here perhaps I need to digress a little. This n plus 1 factorial is actually equal to n plus 1 times n factorial. By definition. Not by definition. You can show that n plus 1 factorial is nothing but n plus 1 times the quantity n factorial, meaning the factorial of 1 less than that. Let me ask you, if that is the case, how else can you write n factorial as? Would you agree? N factorial can be written as n times the factorial of 1 less than that, which is n minus 1 factorial. So n factorial is equal to n times n minus 1 factorial. You want a slightly more concrete example? Okay, 5 factorial is nothing but 5 times 1 less than 5 is what? 4. 4 factorial. 5 times 4 factorial. 8 factorial. 8 times 7 factorial, and so on. That's the whole idea. So we can rewrite this n plus 1 factorial as n plus 1 times n factorial. In the same way, we can write the 2 to the n plus 1 as 2 to the n times 2 to the 1. Do not say 2 to the n plus 1 is 2 to the n plus 2 to the 1. No, it is not. 2 to the n plus 1 is 2 to the n times 2 to the 1. Because a to the m plus n is a to the m times a to the n. That's the concept we applied. Why did we do that? So we can see that 2 to the n and 2 to the n cancels out. This n factorial cancels out with n factorial here, and leaving us with, we can pull the 2 out because it's just a constant, and limit of 1 over n plus 1. Limit of 1 over n plus 1 as n approaches infinity, absolute value of that, is clearly 0, because as n goes to infinity, 1 over n plus 1 goes to 0, and so 2 times 0 is 0. Okay, how does this help us? Look at the test. If you find the limit of absolute value of a sub n plus 1 over a sub n, and that limit happens to be less than 1, is that the case here? 0 is clearly less than 1. Oh, we are done. The series converges according to the ratio test. As simple as that. So, if you decide to apply ratio test, figure out limit of a sub n plus 1 over a sub n, and based on what that limit turns out to be, if it happens to be less than 1, series converges, greater than 1, diverges, equal to 1, inconclusive.